Welcome to another unit on the simplex algorithm. Let's have a look at the exercise. Here we simply have, by using the simplex algorithm, calculate the optimal solution to the following linear problem. We have a maximization problem with the goal function 3x1 plus 4x2. In addition to this, we have some constraints so that x1 is smaller than 12, x2 is smaller than 12 as well, and that 4x1 and 6x2 is smaller than 60. In addition to those three normal inequalities, we also have the non-negativity constraints that both decision variables should be positive, which is this one here. So, having this exercise, what we should do is use the simplex algorithm to find the optimal solution. So we first have to get this problem into a working tableau. That's what I'm going to do on the next slide. So we start with this. Now we're going to build, based on this, a new tableau. Whereas for each decision variable, so here we have two, x1 and x2, we make a new column in our table. So we have the x1, x2 column. Then we make one row for the goal function, the objective function, and we make one additional row per constraint. So we have three constraints, so we add three additional rows here with those variables which we make to cover for the inequalities we have here. So we have x3 for the first one, x4 for the second, and finally x5 for the third constraint. Since all of these constraints are already smaller or equal to constraints, we would not have to adjust them. So we can start with copying our coefficients into our table. We start with the objective function. So here we have a maximization problem. So we take the coefficients from the objective function and we change their signs. So instead of +3 and +4, we're going to work with -3 and -4. So that's why we have here the minus, the negative values. Then we're going to insert x1 and x2 equal to 0 into the objective function. If we do this, we get a value of 0 for the starting solution. Since, as I said, we have smaller or equal to constraints, we can simply take the coefficients we have here and the right side values we have here into our table. Well, first constraint, it's 1x1 plus 0x2, since there is no x2, smaller or equal to 12, so I have 1x1, 0x2, and a 12 on the right side. So for the other two, I do exactly the same. Here I have 0x1 plus 1x2, so 0, 1, and 12 on the right side. 0, 1, 12 on the right side. Here it's a bit easier. I have 4, 6, 4 for x1 column, 6 for x2 column, and 60 on the right side. So with this, I've fully prepared my table. Now I can check whether this starting solution is actually a feasible solution. So have a look here on the right side on these values. And if they are positive or 0, then I know that my solution is feasible and I can start with my simplex. Well, in this case, all three values are positive, so I'm good to go. Starting with the simplex, I first have to find my pivot column and then the pivot row. Pivot column, I take a look here at the line, at the row for the objective function, and I can select those columns where I have a negative value, but ideally I start with the column which has the largest negative value, which in this case is the 4. 3 is a bit smaller than 4, so -4 is absolutely speaking larger than -3, so I select x2 as the pivot column. In the pivot column, I take a look at these values here, and in particular on those or at those values where I have non-negative values which are not 0, so positive values. So this 0 does not qualify, but the 1 and the 6 do qualify. So those two could theoretically be pivot rows. Then I do the following calculation. I take the right side value divided by this value here. So I have 12 divided by 1 gives 12. 60 divided by 6 gives 10. Of these, I select the smallest one, which would be here the 10. So the x5 row will be my pivot row. So I have pivot column x2, pivot row x5, and thus a pivot element of 6. Well, with this pivot element, I can now do my simplex recalculations. For this, I prepared the next table. The first step, I'm going to change or exchange the variables in the pivot column and row. So I exchange x2 and x5, looks like this. Then for the pivot element, I go with 1 divided by pivot element. So here I have 1, 6. For all the other values in the pivot row, I'm going to simply divide them by the pivot element. So I go 4 divided by 6 and 60 divided by 6, giving me 2/3 here and 10 here. For all the other values in the pivot column, I'm going to divide them by minus pivot element, so by minus 6. So 1 divided by minus 6 gives me minus 1/6. 0 divided by minus 6 still stays 0. And minus 4 divided by minus 6 is plus 2/3. So I'm done with the easy part. Now for all the other values, meaning those two, this one, that one, and those two, I need to use some rectangular form of recalculation. But before I get there, I can actually use some way to simplify the calculation. Because whenever I see that in my pivot column or pivot row, there's a 0, this will simplify things significantly. As it turns out, here in the pivot column, I have a 0. This means that all the values in the respective row will remain the same. So here I have 1, here I have 12, so I will just copy the 1 and the 12. With this taken care of, we can continue with recalculating all the other values. First, I would start with this value up here, because then I can see whether I already am at the optimal solution. As I said, we can use this rectangular form of recalculation, which means I consider the value I want to change and the pivot element as two opposing corners of a rectangle. Meaning I have here these 4 corners. They are opposing, and then I have those two as well. For the recalculation, I take the element I want to change minus these two multiplied divided by pivot element. So in my situation, I go with minus 3 minus minus 4 times 4 divided by 6. Minus minus makes it positive, so minus 3 plus 4 times 4 divided by 6, which in the end will give me minus 1/3. This is not yet positive, so I still have to continue by calculating all the other values. If both of these entries would have been positive, I would have arrived at my optimal solution and I could have saved a little bit on recalculation. But more on this a little bit later. Well, as I said, I have to recalculate all the other values, so meaning these and these two. And in each of these cases, I again do the same way with the rectangle which I proposed before. So for example, with the 0, this would be my rectangle. And I would go by calculating 0 minus minus 4 times 60 divided by 6. Minus minus again gives plus here. So 4 times 60 divided by 6 gives me 40. I can do the same thing for this 12. I would have this rectangle. For this 12, this rectangle. For this 1, I would have this rectangle. And for this 0, I would have this rectangle. One thing to keep in mind, and also to, well, in some way control whether I'm going in the same right direction, did my calculations correctly. Well, I don't know whether all these values I calculated correctly. One indicator that I work in a decent fashion, applied the simplex in a way it's supposed to be applied, is that the value of the objective function increases. So as soon as I use the standard simplex, this value, at least for maximization problems, should always increase. For minimization problems, it should always decrease. So that's one thing to keep in mind. Well, as I said, with all the recalculations, I see here I'm not yet finished. I still have one column with a negative value in the objective function. So I'm going to select this remaining column as pivot column. And I consider all these values here which are positive. So this only qualifies the 1 and the 2/3. And then I'm going to divide 12 by 1, giving me 12. And 10 by 2/3. Well, instead of dividing by 2/3, I can also multiply with the inverse. So multiply with 3/2, giving me 15. Well, in this case, 12 would be smaller. So I select 1 as the pivot element. And for the recalculation, I will turn to the next slide. So here I have the same one. Do my recalculation based on this pivot element. So first I exchange the variables in pivot column and row, so x1, x3. Then for the pivot element, I'm going to divide 1 by the pivot element. Well, it stays 1. I divide everything in pivot row by the pivot element, so I divide everything by 1, so nothing changes here. And everything in the pivot column is divided by minus pivot element. So since it's minus 1, only the signs will change. For all the other values, I'm going to use the rectangle form again. However, I see here pivot row has a 0, so I can simply copy this column as is, making my life a bit easier. So I only have to recalculate these values here, but then again I see I have only positive values up here. So I know I already arrived at my optimal solution, meaning I would not necessarily have to calculate the value for x4, because this is not one of my decision variables, so I would not require this value necessarily. But I still need to calculate first this value, then that value. Well, for the 10, changing the 10, which I still require, I would have this rectangle. So I would calculate 10 minus 2/3 times 12 divided by 1, giving me 10 minus 8, which is 2. For this value up here, I would have this rectangle, which would be 40 minus minus, so getting plus, 1/3 times 12 divided by 1, so 1/3 times 12 is 4. 40 plus 4 gives 44. Well, as I said, this is my optimal solution. In the optimal solution, the variables up here will have a value of 0. The values here will have the values on the right side. So my decision variables x1 and x2 have a value of 12 and 3 respectively, whereas those two constraint variables have the value of 0 and x4 has a value of 4. In total, the objective function will take on a value of 44. So if I choose x1 12, x2 2, under the constraints I will have an optimum with an optimal objective function value of 44. Well, that brings me to the end of this session, so I hope you enjoyed. I say goodbye and see you next time.